Welcome to the third video on first order responses. This video is going to look at step responses with a non-zero initial condition. So first, a reminder of some of the things that were said in the first two videos. We're going to consider a system which can be modelled by a first order differential equation with constant coefficients. So without loss of generality, this can be written in the following form: t dy dt plus y of t equals k u of t. Now this was covered in the earlier videos, so we'll say no more for now. What we want to look at is how does y of t behave for positive time when u of t is a step and the initial condition y of 0 is not equal to 0. What we want to look at is how the behaviour depends upon the coefficients t and k, because these are the only two parameters in this particular model. We'll also look at the effect of the initial condition in the input, but we're most interested in the impact of t and k. Now, just a reminder, if you haven't looked at the first two videos on first order systems, I recommend you go through those before you continue, because we will take some things for granted that were covered in those two videos. Video 1 looked at first order system responses with no input but a non-zero initial condition. And video 2 looked at first order system step responses with 0 initial conditions. In this video, we're going to consider the cases where there is a non-zero initial condition and a step input. So here we go. What principle are we going to use? We're going to use the principle of superposition, which holds for linear systems. Basically what that says is if the response of a linear system to u1 can be computed, and you can also compute the response to a different input u2, then the response to input u1 plus u2 will be a sum of the two responses calculated separately. So let's look at what this means for the particular case we're interested in. We've got a response with initial conditions, non-zero initial conditions, but no input. That's that box there. And we've got a response with 0 initial conditions, but a step input. And what we're saying is if you want to get the total response to the first order model, then you can simply add these two responses together. And that's basically linked to linearity. There are a set of videos on linearity if you want to check those out. So here we go. The system goes from an initial condition to a steady state with a given exponential decay. And what we want to work out is exactly how does it do this. Well, this box shows you what was covered in lecture 1. If you have non-zero initial conditions but a 0 input, how does the system behave? And you remember we got this behaviour x of t equals a e to the minus time over capital T, where a was the initial condition, capital T the time constant. Okay, what if we had a 0 initial condition and a step input? Then we got a response like this: x of t equals k times 1 minus e to the minus t over t. So therefore, if we want to find the response with a step input and a non-zero initial condition, we just add these two together. So here we go. You'll see the total response written down here. There's the bit that came from the left-hand box, if I draw an arrow to show where it's come from. And there's the bit that's come from that box. So we've simply added the response for a non-zero initial condition, no input, to the response for a step input with a 0 initial condition. Now, as it happens, both of these terms include an exponential. So people normally group the two exponential terms, there they are, a minus k times e to the minus t over t plus k. Now this helps us because what can we see? We can see this term with the e to the minus t over t gives us the decay. How quickly does this signal converge to its steady state value? Whereas the other term gives us the steady state. Okay, so there's a nice separation in the solution between a bit that changes and a bit that is constant. Now you might want to verify this solution and say, okay, can you just prove to me that this is definitely true? Well, the easiest technique for this is very simple. Simply take this x of t and substitute it into the original differential equation and verify that the equation is solved. So here we go. there's the proposed solution, x equals a minus k e to the minus t over t plus k. If I differentiate that, I get this term here. And what I'm going to do is I'm simply going to substitute that x and that dx dt into this differential equation up here and check that it's solved. So here we go. T dx dt plus x equals a minus k e to the minus t over t plus k, so that's the x term, plus t times a minus k over minus t e to the minus t over t, and that's the dx dt term. Now what you'll notice, hopefully, is this t here will cancel with this t here, so you end up with an a minus k, but there's a minus underneath, and so you'll then notice that this term will cancel with this term. So you get left with t dx dt plus x equals k. So we verified that our proposed solution does indeed satisfy the original equation. If you want to do a more formal derivation, then this will be covered as part of a mathematics module as beyond the remit of this particular set of videos. However, a quick summary of the type of technique you might come across: you assume the solution is exponential, plus a part matching the structure of the input. And then you find parameters which essentially make that structure fit. I won't say any more, so we'll leave that to your maths lectures. But what we will do on the next slide is we'll do an alternative derivation using Laplace methods. So here we go. If we take the Laplace of our original differential equation, so there we've got it, we've got here t dx dt plus x equals ku. Then if we take the Laplace of x of t equal to x of s, the Laplace of u to be u of s equals 1 over s, and we put all that together, and you'll see this was covered in the first two videos, we get st plus 1 times x of s minus capital T x of 0 equals k over s. And I can then rearrange all of that to give me x of s equals this term over here. Okay, so that's straightforward Laplace. We won't dwell any more on that and suggest you look at the videos on Laplace if that went a little bit too quickly. Next we want to do inverse Laplace to solve the corresponding x of t. So here we go. We've got this term here, which is what we had on the previous slide, and what we're going to do is we're going to say that if I put this into partial fractions, I'm going to get a c1 over s plus a c2 over s plus 1 over t. Now I've just written the solution down. Here it is, k over s minus k minus x of 0 over s plus 1 over t. So I've not derived that formally. If you want to do the partial fractions in full, please look at the other video and that will show you how to prove that this is true. Having done the partial fractions, you can of course now solve by inspection. The inverse Laplace of k over s is just k, and the inverse Laplace of k minus x0 over s plus 1 over t is here, k minus x of 0 times e to the minus t over t. And you will notice this is unsurprisingly the same solution as the one you had before. Now, some obvious observations. X of t begins with the correct initial condition, so if I substitute t equals 0 into this equation, then clearly e, if I put this e to the 0 equals 1. So therefore, what you will get, x of 0 equals k minus k plus x of 0. In other words, x of t equals x of 0 at t equals 0. Exactly what you expected. So the solution starts from the correct initial condition. If you now say, okay, what happens as time goes to infinity? Well, what you've got is the limit as time goes to infinity of e to the minus t over t equals 0. So in other words, as time goes to infinity, this term here disappears and you get left with just k. So k is the steady state. So we've got two clear observations from this solution. We know where it starts, we know where it finishes, and the only dynamics in the equation is this exponential, so it must follow an exponential curve from the start point to the end point. So what use is this response? So there's a clear link between the behaviour and the parameters. And what does this mean? It means that we can actually choose the parameters to achieve the desired behaviour. because we know exactly what impact those parameters have on the behavior. We know that k gives us the steady state. We know that t dictates the speed of the exponential. We also recognize that systems of a given form must all have the same behavior. So any system which I can write down as a first order model must all have solutions of this form. They go from the initial condition to the steady state following an exponential curve, and that's very valuable. And finally, something that was covered briefly in the previous video, we can estimate the model parameters from the behavior. So if you don't know k and t, but you can do a step response of a real system and you know the underlying model is first order, you can estimate k and t from that response. So what have we got now? A summary of some key components before we move on. Here's the model. T dx dt plus x equals ku. That's our first order model, and we're assuming that the input is a step. Here I've written a over s, so a step of magnitude a. For this type of model, the response is given as x of 0 minus k times capital A e to the minus t over t plus ka. So that's what we've learnt in this particular video. Okay, a bit of thinking about this. The steady state depends upon the system gain k and the magnitude of the input a. So there it is. The steady state value of x is k times a, and k is normally considered as the system gain. It's the ratio of the steady state output to the steady state input. The initial condition clearly appears in the response, and this is unsurprising, so there it is. The dynamics, or the speed of the response, are determined by the exponential term and depends solely on the time constant, capital T. So there you can see that here, there's an e to the minus time over capital T, and that governs how fast the x of t gets to its steady state value. And finally, how far does the system move? Well, again unsurprisingly, it goes from the initial condition, x of 0, to the steady state, k of a, and so what you can see is the distance of movement is given by x of 0 minus k times a. And for convenience, I'm going to use it in some later slides, I'm going to determine this, or rather define this value here, d equals x of 0 minus ka, which gives me the total distance moved by this first order response. So there we go, circled it again. An example. Determine the response for 6 dx dt plus 4x equals 3 and x of 0 equals 2. So the first step is we need to put the model into time constant form, and you'll recognize this one by now. I think we've done it on the previous videos. So we've got 6 over 4 x dot plus x equals 3 over 4, and so I've got t equals 1.5, and in this particular case k and u were all linked together, so I've got ka equals 0.75. Okay, so I know the steady value is 0.75, I know the time constant is 1.5, and I know that x of 0 equals 2. So if I want to write my solution down, I can now write x of t equals, and I'm going to have x of 0 minus ka into e to the minus t over t plus ka, and then I can put in the numbers. So for this particular case I have 2 minus 0.75 e to the minus t over 1.5 plus 0.75. Okay. Another example. So here we've got 0.2 dx dt plus x over 3 equals 0.45 and x of 0 equals minus 2. So again, the first thing to do is put the model into time constant form. So here I've got to multiply by 3, so I will get 0.6 x dot plus x equals 1.35. So I've essentially multiplied every term in the equation by 3 so that the coefficient of the x is 1. So what I've got now is t equals 0.6 and ka equals 1.35. So next I can write down the solution in its standard form. So I've got x of t equals x of 0 minus ka e to the minus time over capital T plus ka. And now put in the values. So I've got minus 2 minus 1.35 e to the minus t over 0.6 plus 1.35.